Hello, I am Professor Annakkage from University of Manitoba in Canada. This is my second lecture on power system dynamics. In this lecture, I will show you how to develop a small signal model of one machine connected to an infinite bus system using the equations developed in my previous lecture. I will present the model in state space form as well as the transfer function form, and then I will use the transfer function form to design a power system stabilizer. In my lecture 4, I will explain how to use the state space methods to design power system stabilizers. We derived these three differential equations for the synchronous machine in the last lecture. Two equations for rotor dynamics, the first two equations, and the third equation for field flux. Note that in the second equation, the term Tm on the right hand side is the mechanical driving torque exerted by the prime mover. We treat it as an input to the model. In the third equation, the term EFD is the voltage applied to the field winding. We treat this as another input to the model. Later on in this lecture, we will learn how to extend this model considering the fact that EFD is the output of the excitation system and it is not a direct input. So for the time being, both Tm and EFD are treated as inputs. You have seen this first equation in the previous lecture. It gives a relationship between the DQ frame voltages and DQ frame currents from the point of view of the synchronous machine. Now let's look at the second equation. The machine is connected to an infinite bus through a transmission line. Its resistance is RL and the reactance is XL. EB is the infinite bus voltage. If we take the infinite bus voltage as the reference, its imaginary part is 0 and the real part is EB. So the Q and D components of the infinite bus voltage are EB cos delta and EB sin delta. You can easily verify using RI to DQ transformation you learned in the previous lecture. This second equation relates DQ voltages and DQ currents of the machine from the point of view of the network. If we linearize these equations for small changes of voltages, currents, and delta and EQ prime, we get these equations. Now I want to introduce you to small signal linearized model by giving you 4 exercises. The first exercise is to eliminate delta EQ and delta ED from equations 84 and 85 and obtain expressions for delta IQ and delta ID. You should be able to show that delta IQ and delta ID can be expressed as shown in these equations. And then the second exercise is to linearize the 3 differential equations of the machine and show that we can obtain these differential equations for small changes of variables. The third exercise is to eliminate delta IQ and delta ID in the linearized differential equations using the result of the first exercise and show that we can obtain the state space model shown here. You see in this equation there are some k values k1, k2, k3 and k4 and those k values are given by these equations. And the fourth exercise is to show that the state space model can be represented by the control block diagram shown here. The output of this control system is a change in rotor angle delta delta. The two inputs are delta Tm, a change in mechanical driving torque, and delta EFD, a change in the voltage applied to the field. The transfer function K3 over 1 plus ST3 represents the dynamics of the field winding, and the transfer function 1 over Kd plus 2Hs represents the dynamics of the rotor. The input to this transfer function is the change in acceleration torque, which is delta Te minus delta Tm. We are going to investigate the dynamic behavior of the machine using this control block diagram. We will pay attention to the delta Te component that gives rise to the change in acceleration of the rotor. Before we go into this analysis, I want to give a review of the dynamic behavior of a simple second order system. The second order system described by this equation represents simple harmonic motion for positive values of A. That means when x is disturbed from its equilibrium position of x equals 0, the variable x will undergo constant amplitude oscillations, and the frequency of those oscillations will be square root of A in radians per second. Now if we add a term proportional to the derivative of x, and if b squared minus 4a is less than 0, this system will show damped oscillations when x is disturbed from its equilibrium state of x equals 0. The equation at the bottom is the standard way of writing the first equation. In this equation, omega n is the natural frequency of oscillations in radians per second, and psi is the damping factor. We can show that the equation of rotor dynamics of a synchronous machine has the same form. For small changes of delta, Tm and Te, we can write the equation for rotor dynamics as the second derivative of delta delta equals omega naught over 2h times change in Tm minus change in Te. For constant mechanical torque, delta Tm is equal to 0, and we get this second equation. Now if delta Te is in phase with delta delta, this equation represents simple harmonic motion. But delta Te is not in phase with delta delta. We will see this in the next few slides. Typically, delta Te has a component in phase with delta delta and another component in phase with delta omega. These two components are in quadrature. Delta omega, being the derivative of delta delta, leads delta delta by 90 degrees. The component proportional to delta delta has the effect of pulling the system back to the equilibrium. In the context of a synchronous machine, it tries to keep the machine in synchronism. So we call Ks the synchronizing coefficient, and Ks times delta delta, the synchronizing torque. Similarly, Kd is called the damping coefficient, and Kd times the derivative of delta delta is called the damping torque. Positive values of both components is essential for maintaining the stability of the synchronous machine. Now, referring to the control block diagram, the component of delta Te due to any changes in the field flux is given by K2 times delta Eq, and it can be expressed as negative value of K4, K3, K2 divided by 1 plus St3 times delta delta. At steady state, by setting S equal to 0, it simplifies to negative value of K4, K3, K2 times delta delta. Again, referring to the control block diagram, there is another component K1 delta delta. So the net synchronizing torque is K1 minus K4 times K3 times K2 delta delta. And if this is positive, the machine is stable from steady state point of view. In other words, when the rotor angle is disturbed from its equilibrium, it will come back to the equilibrium. In the previous slide, we discussed the synchronizing torque at steady state. Under transient conditions, when the machine is oscillating at some frequency other than 0, the contribution of field flux variations into the electromagnetic torque has two components. One component proportional to delta delta and the other proportional to delta omega. These are the synchronizing and damping torque components of the electromagnetic torque, as shown in this last equation. A good example to calculate the oscillation frequency, synchronizing and damping torques is found in the chapter 12 of Power System Stability and Control by Dr. Prabha Kundur. So I am reproducing that problem here, that example here. Here we have a synchronous generator connected to an infinite bus through a transformer and a transmission line. Infinite bus voltage is given. The impedances of transmission line and the transformer are also given. And the generator is supplying 0.9 plus J 0.3 per unit power to the infinite bus. Synchronous machine inductance values are given and the transmission line parameters are given, and also the time constants TDO prime and inertia constant given. Now we can use the equations that we derived in the previous slides to calculate K values and T3. Then we can compute the eigenvalues of the system matrix A. We will get a negative real value and a pair of complex conjugate eigenvalues. The real eigenvalue is negative and the real part of the complex conjugate pair is also negative. Therefore, we conclude that the system is stable, and if we disturb the system from its equilibrium, it will undergo damped oscillations, and the frequency of these oscillations will be 6.41 radians per second. We can calculate the steady state synchronizing torque coefficient using the equations derived earlier. We find that the steady state synchronizing coefficient is positive, is equal to 0.3679. We can calculate the synchronizing and damping torque coefficients. Again, we find that they are both positive This is expected because from the eigenvalues we found that the system is stable. So far in our model we have treated the field voltage EFD as an input to the system. But we know that EFD comes from the excitation system. Our next task is to extend the model to include the exciter. The function of the exciter is to provide the field voltage. The amount of voltage applied to the field voltage, to the field winding, is determined by the error between the measured and the desired terminal voltage. By increasing the field voltage, you can increase the terminal voltage, and by decreasing, you can decrease the terminal voltage. The terminal voltage ET can be expressed in terms of D and Q components as ET squared equals ED squared plus EQ squared. And now for small changes, we can linearize that equation and obtain the equation at the bottom of this slide. Here the superscript naught represents the value of the variable at the equilibrium point. Now here is another exercise for the students. Using the previously derived relationships between dq components and state variables, so that delta ET can be expressed as delta ET equals a constant K5 times delta delta plus another constant K6 times delta EQ prime. The two variables P1 and P2 in the equations for K5 are given by these two expressions. Now, to demonstrate how to incorporate the model of an exciter, let's assume a simple exciter transfer function Ka over 1 plus STA. Gain is Ka and the time constant of the excitation system is Ta. The input to the exciter is the error between the desired and actual terminal voltages, delta Vref minus delta Et. And we can write this transfer function relationship in the form of a differential equation to obtain this last equation. So this equation gives a differential equation for delta EFD. This equation adds another differential equation to the third order model to make our system a fourth order system. Now combining all four differential equations, we get the state space system given here. And again, note that the input to this state space system are delta Vref and delta Tm. In our third order model, the two inputs were delta EFD and delta Tm. This state space system can be translated to a control block diagram form. I will leave this as an exercise for the students. Again, note that the two inputs are delta Vref and delta Tm, and the output is delta delta. Now from the control block diagram we can obtain this expression for delta Te due to the excitation system. From this we can derive a transfer function between delta Te and delta delta, and that transfer function we refer to as Hs. If we know the k values and time constants, we can compute Hs for a given eigenvalue of the system matrix by substituting S equals sigma plus j omega, where sigma plus j omega is an eigenvalue of the system matrix A. The real part of Hs gives the synchronizing torque coefficient due to the exciter, and the imaginary part gives the damping torque coefficient due to the exciter. Okay, now we are ready to design a power system stabilizer for one machine connected to an infinite bus system. The power system stabilizer, or PSS, is an additional controller in the exciter control system. The PSS injects a signal to change the voltage reference or to modulate V reference so that we can damp out low frequency oscillations, and they are typically less than 3 Hz. We learned that to provide damping, we must add a torque component in phase with delta omega into the electromagnetic torque Te. There are many ways of deriving this signal, but in this lecture we will use the speed deviation as the input signal to the power system stabilizer. This block diagram shows a power system stabilizer that uses the speed deviation delta omega as its input. The first block is the gain of the PSS. The second block, the washout filter, is a high-pass filter that blocks PSS from responding to steady-state frequency deviations. The time constant of the washout filter must be large enough to let the frequency at which the damping to be introduced pass through it. Since the PSS signal is applied at the input to the exciter, the contribution of the signal to Te will lag the input signal. This phase lag is compensated by introducing a phase lead using the third block. Sometimes, when we have to introduce a large phase advance, we use 2 or 3 phase compensator blocks in series. The required amount of phase advance can be determined by analyzing the influence of power system stabilizer on the damping torque component. From the control block diagram, we can write this equation, and then by rearranging the terms in this equation, we can obtain delta EQ prime to have two components, one component due to delta Vs, which is the power system stabilizer signal, and the second component due to delta delta. To design the power system stabilizer, we are interested in the transfer function T1. Now, if we substitute the frequency of electromechanical oscillation for the variable S in transfer function T1, we will obtain T1 as a complex number, and we express that complex number in polar form, and the angle of this complex number is the required amount of phase advance. After we determine the required amount of phase advance, we have to design the phase compensation block. If we express the phase advance block in the general format in terms of variables alpha and t, as shown in the equation at the top of this slide, then this transfer function has the maximum phase angle phi max at frequency of omega equals 1 over t times square root of alpha, and we can also show that maximum phase angle phi max is given by sine inverse alpha minus 1 over alpha plus 1. Here omega is the frequency of the electromagnetic oscillations in radians per second. We can solve these two equations to determine the time constant of the phase advance block. So here is an exercise for the students. Determine T1 and T2 to obtain a phase lead of 50 degrees at the frequency of 0.8 Hz. The transfer function relationships in the PSS can be translated into differential equations, just like how we did that with excitation system model. Now I like to show an example of designing power system stabilizer. We have one machine connected to an infinite bus system with all the k values and time constants and inertia given. So the steps involved in designing the power system stabilizer is, first you express delta EQ prime in this form, and then delta Vs is the PSS signal, and here we are assuming that we are designing a power system stabilizer to damp oscillations at 1 Hz. So from the control block diagram, as we did earlier, we can derive the transfer functions T1 and T2. And we are interested in the transfer function T1. And also the frequency of electromechanical oscillations that we want to introduce damping to is 1 Hz. So S equals J times omega, or J times 2 pi. Now we substitute S equals J times 2 pi into the transfer function T1S and obtain T1 as a complex number in polar form, and its phase angle is negative 117.9 degrees. So we know that to compensate for that phase lag, we have to introduce a phase advance of 117.9 degrees. Compensators are typically designed to have maximum phase angle of 60 degrees. So here we are going to use two identical blocks, with each block giving 58.95 degrees phase advance. So following the steps I described earlier, you can express maximum phase angle of that compensation block as sine inverse alpha minus 1 over alpha plus 1, and we know that angle must be 58.95 degrees. So you can calculate alpha. So in this case alpha is 12.96, and then using the equation for omega, we know omega and alpha, we can calculate the time constant T. So the time constants of the phase lead compensators are two identical compensators. So T1 equals T3 equals alpha T, which is equal to 0.57 seconds, and T2 equals T4, also equal to T, is 0.044 seconds.